Okay, so after looking at example 1, where we're taking out the largest perfect square factor, we're going to take a look at some other examples as well. So in number 1, there's lots of ways to break up 50, but our goal is to find the largest perfect square factor. So we could break up 50 as 5 and 10, but neither one is a perfect square. Rather, we're going to go with 25 and 2. Now the square root of 25, we know, so we can take the square root of 25 and bring that out as a 5. But the 2 we don't know, so we're going to leave that inside the radical. Now x's and variables. We know that the square root of x squared is x. So if we have a x squared and another x squared, okay, the square root of x squared is x, and the square root of x squared is x, giving us x squared. We know that the square root, let's do x to the third. The square root of x to the third is the square root of x squared with another x. Now the square root of x squared is x, and then we have the square root of x left inside. So if we have x to the fifth is like x to the fourth times x. Now the square root of x to the fourth, we've got two groups of within 4, we get x squared, and with an x left over on the inside. So actually I'm going to take this x to the fourth out, and we've got an x left inside. And then y squared, the square root of y squared, similar to this, the square root of something squared is just itself. So our final answer is 5x squared y square root of 2x. All right, let's take a look at 60. 60 can be broken up into a perfect square. Now, we could break it up as 2 times 30, but neither one's a perfect square. But 4 times 15, and 4 is a perfect square. So when we take the square root of 4, that will come out as a 2. And the 15 is going to stay inside. A to the 7th. We want to know how many groups of 2 are in 7. There's 3 groups of 2, so we have a to the 3rd with 1 left over. In b to the 6th, when we're taking the square root, we're taking groups of 2. So how many groups of 2? There's 3 groups of 2 with none left over. So this is our final simplified radical form. 18 can be broken up many ways as well. 18 could be 2 times 9, and 9 is a perfect square. So we've got 2 times 9. We can't take the square root of 2, but we can take the square root of 9. And the square root of 9 is 3. The 2 is going to stay inside. And then x to the 9th. For x to the 9th, we want to know how many groups of 2 we have. We have 4 groups of 2 with 1 left over. In y to the 3rd, we want to know how many groups of 2. We have 1 group of 2, but we don't need to write a 1. It's invisible, with 1 left over. All right. With 45, when we're taking the square root of 45, we want to break it up into numbers that have perfect squares. So yes, it's 3 times 15, but neither one's a perfect square. Rather, we've got 9 times 5 is 45. We know the square root of 9, so the square root of 9 is 3, and 5 is going to be left inside. Now, x to the 25th, we're finding how many groups of 2 are in 25. Well, we've got 12 groups of 2 with 1 left over. And y to the 16th, we want to know how many groups of 2 are in there, so we have y to the 8th. Okay. All right, number 5. In number 5, we want to break up 112 into a perfect square factor times something else. And perhaps with 112, you're not very familiar with what would be a perfect square factor in here. So we're going to go ahead and do a prime factorization tree. This is helpful when you're not picking out that perfect square right away. So 112 we know is divisible by 2, and we have 2 and then 56. All right, we know 56 is divisible by 2. And when we divide by 2, we get 28. Now we know 28 is divisible by 2, but we also know it's divisible by 4 times 7. Okay, if we take a pair of numbers, 2 times 2, that will get us a perfect square, which is 4. But now we have 4 times 4. So 112 is really 4 times 4 times 7, which is 16 times 7. And there we just found our largest perfect square factor. Okay, so the 16, we can take the square root of that, and we get 4 with the 7 left inside. Now a, that's a to the first, there's no pairs, so the a is going to be stuck inside. And b to the 12th, we're taking out the pairs, and there's 6 pairs. Well, we left ourselves a little too much space there, so let's rewrite this as 4b to the 6th square root of 7a. All right, go ahead, pause the video, and try 6, 7, and 8 on your own, and then come back and finish it out. Okay, welcome back. For number 6, we broke this up to 25 times 3. We know the square root of 25, which is 5, but we don't know the square root of 3, so we're going to leave it as 5 radical 3. All right, 72. There's lots of ways to break up 72. A lot of students are tempted to say 9 times 8, which is true, except 8 has a perfect square factor. 8 is 4 times 2. Now we know that a perfect square times another perfect square will get us a perfect square. So 9 times 4 is 36. So really, 72 is 36 times 2. So I'm going to take 36 times 2. All right, the 2 and the x on the outside, they're going to stay on the outside. Now this is saying 2 times x times whatever's in here. So when we bring out, and we have the square root of 36 times 2, we can break this up to x to the 10th, x to the 1st, because we want pairs, y to the 22nd, and y to the 1st. Okay, so when this 36 comes out, it comes out as a 6, and it's going to multiply with whatever's left outside, or is already outside. The 2, leave some space, the 2 stays inside. X to the 10th becomes x to the 5th. Y to the 22nd becomes y to the 11th. Y to the 11th. And we have an x left over, and we have a y left over on the inside. Now on the outside, we're going to combine what we can. When we're multiplying, we got 2 times 6 is 12. When we multiply variables with the same base, we add the exponents, and then we have y to the 11th, the square root of 2xy. For number 8, when we're working with fractions. When we're working with fractions, we don't want fractions in our radical, but we can clean up what's inside here. The b cubed and b, when we're dividing, we subtract the exponents. So really we have the square root of 16a to the 9th b squared over 9. Now we also learned in the first part of the video that we have the quotient rule. The quotient rule says that we can take the square root of the top divided by the square root of the bottom. Now this is going to work out really nice because 9 is a perfect square and we can't have radicals in our denominator. But we can go ahead and take the square root of the top, which the square root of 16 is 4. A to the 9th, we're finding pairs. We have 4 pairs with 1 left over. B to the square, we want to know how many pairs we have. We have 1 pair with none left over. And then the square root of 9 is 3. Now 1 exponents are invisible, so we don't need to write those. And there's our final answer. Number 9. In the example number 9, we're going to take what's outside and multiply with what's outside. So we've got a 2 and a 4 that are both on outside. Now, as a reminder, everything here is being multiplied. 2 times the square root of 3x times, 2 parentheses next to me means times, 4 times this. It's all multiplication. So multiplication is commutative. We'll take the 2 times the 4 and we get 8. And then what's inside the radical and inside the radical, we're going to multiply those together. 3 times 12 is 36. We have x to the 8th. Now we can go ahead and clean up the inside. When we take the square root of 36, we get 6. It's going to multiply with what's already out there. And x to the 8th is x to the 4th. So 88 times 6, it's not 86. 8 times 6 is 48. X to the fourth is our final answer. All right, pause this video and try number 10 on your own, and then come back and check your answer. Okay, so our final answer here is 20x to the 20th, y to the 23rd, square root of 2xy. 32 broke up to 16 times 2, and that's why the 4 came out. And then we take out the pairs and the exponents. All right, this is simplifying square roots. We're going to be working on simplifying cube roots next. Practice a couple of these, and then we'll come back for the next video.